In our technological journey, we saw that data centers play a crucial role for artificial intelligence. Indeed, integrating cloud computing and AI algorithms in the machine learning as a service approach allow to simplify the design phase, since advanced machine and deep learning solutions can be used without requiring a high expertise in the field, and the operational phase, where machine and deep learning as a service solutions can be quickly moved from the design phase to the market by also supporting the scalability of the solutions. On the other hand, a cloud computing approach to AI suffers from some drawbacks. Moving all the acquired data to the cloud for the AI processing requires a high bandwidth and a permanent interconnection, a technologically challenging situation in the application scenarios where connection is scarce or absent. In addition, the transmission phase is the largest one in terms of power consumption, much more power-hungry than acquisition and processing of data. Furthermore, moving the acquired data to the cloud could induce privacy or security issues when personal or sensible data are considered. Last, but absolutely not least, acquiring data, moving them to the cloud for the processing, and waiting back for the results might introduce unforeseen latency with which a decision is made. This makes cloud-based processing of AI not feasible in the application scenarios where real-time or near-real-time decision must be made, such as raising an alarm or detecting potentially critical situations. To address these problems, the scientific and technological trends we are seeing reside in the ability to move the processing, and in particular the intelligent processing, as close as possible to where data are generated. Let's see how this novel paradigm can be moved from the cloud to the ground. As we have already analyzed, the AI hardware comprises Internet of Things, embedded personal computers, and edge computing systems. The core of these technological families resides in the ability to operate on the field in a pervasive manner. Units belonging to these families might differ in computing and memory abilities, or can be endowed with different types of sensors, actuators, or communication modules, but they share the capability to run AI algorithms directly on the field. In the case of IoT, embedded PC, and edge computing systems, the artificially intelligent platforms comprise all the frameworks, toolboxes, and libraries of machine and deep learning algorithms that have been optimized to take into account the constraints on computation, memory, and energy consumption of pervasive units. Examples of such platforms are TensorFlow Lite, Azure for IoT Edge, CoreML, AWS Greengrass. The core of such frameworks is the ability to consider approximation mechanisms to reduce the complexity, meaning that we want to reduce the memory footprint and computational demand of machine and deep learning solutions. To achieve this goal, quantization and pruning mechanisms for machine and deep learning are considered. We will explore these mechanisms in the next video. For now, let's focus on moving the AI processing as close as possible to where data are generated. This approach provides several advantages from the AI application point of view. The ability to locally process the data allows to increase the autonomy at the unit level, since decisions can be made locally, hence without requiring to transmit everything to the cloud for the processing and waiting back for the results. Acquiring and locally processing the data allows also to reduce the latency with which a decision is made, since we are no longer required to wait for the processing on the cloud and the transmission of the results over the internet. In this case, we can process and make decisions as soon as data are acquired. This is crucial for all the real-time or near real-time application scenarios. In addition, if we are able to locally process the data, we can reduce the required transmission bandwidth, since we are required to transmit to the cloud only selected features or KPI. We already commented that transmitting data to the cloud is very power-consuming, hence reducing the amount of data we transmit is of paramount importance to increase the energy efficiency of pervasive units. We emphasize that, from the energetic point of view, locally processing the data is much more energy efficient than transmitting them to the cloud for the processing and receiving back the results. Last but not least, not moving possibly sensitive data to the cloud could increase the privacy and the security of our pervasive system. At this point, we have to address two important questions. Which is the hardware that we are considering for AI? And which are the AI solutions that we could employ on that? If the hardware is simple and tiny, simple AI solutions could be considered. If the hardware is more performing, more complex AI solutions could be employed. But here we have to change our point of view, since pervasive units typically operate within an ecosystem of units that could be heterogeneous in the hardware or in the communication abilities. In such an ecosystem of pervasive units, we can allow the distributed processing of AI solutions, where part of the elaboration is carried out by tiny units that can perform an initial processing of the data, and that can ask more performing units to complete the processing when needed. This moves us to the scenario where the intelligent processing is not limited in the cloud, but it is moved anywhere in the network of units, hence supporting the so-called intelligent computing everywhere, that represents one of the most promising technological and scientific computing paradigms for the next years.